Give me 50 minutes, and I will make differential calculus click for you. Forever. You've heard the terms, right? Derivatives, differentiation. Maybe you've even seen dy/dx written down somewhere. They are the language of change. And honestly, they're non-negotiable for success in a lot of fields. Physics, engineering, computer science, economics, statistics, and of course, deep learning. At the very heart of differential calculus, you find this. Okay, look at this table. This is the toolbox you will master. It probably looks a little intimidating right now. I get it. We've got categories like basic rules, essential functions, trigonometric functions, and then these combination rules down at the bottom. You can see a function, f of x, and right next to it, its derivative, f prime of x. This table is the core of differential calculus. It looks like a random list of rules to memorize. But here's the thing. It's not. By the end of this video, you won't have memorized this table. That's not the goal. No, you will have built it from a single idea. You will understand precisely why the derivative of a function, let's say f of x equals x squared, is exactly 2x. And from that one core insight, you will see how every other rule logically follows. From the master key, which is the chain rule, to the truly exotic stuff, like the derivative of arcsine of x becoming 1 over the square root of 1 minus x squared. No magic, just mechanics. Let's get started. Let's talk about a car's journey. A car's position in meters, we'll call it p, after t seconds is given by a really simple function. P of t equals t squared. So at t equals 1 second, it's at 1 squared, which is 1 meter. At t equals 2 seconds, it's at 2 squared. That's 4 meters. And at t equals 3 seconds, it's at 3 squared, 9 meters. Simple enough, right? But here's the question. What is the car's exact speed at the single instant t equals 2 seconds? And this leads to a huge problem. I mean, think about it. How do you measure speed over 0 time? The formula for speed is distance divided by time. If the time interval is 0, you're dividing by 0, and you can't do that. This, right here, is the central problem of differential calculus, and the tool we invented to solve it is called the limit. The limit is like the microscope of calculus. It lets us zoom in on a single instant by looking at what happens as we get infinitely close to it. So let's try that. We can't calculate the instantaneous speed, but we can calculate the average speed. And the formula for average speed is just the change in position divided by the change in time. Or, as you might see it, delta p over delta t. So let's do a quick calculation for the average speed. Our context is still p of t equals t squared. Let's find the average speed between t equals 2 and t equals 3. First, the change in position. That's p of 3 minus p of 2, which is 3 squared minus 2 squared. That's 5 meters. Next, the change in time. That's just 3 minus 2, which is 1 second. So the average speed is 5 divided by 1, which gives us 5 meters per second. But that's a really crude average, isn't it? It's over a whole second. To get closer to the speed ATT equals 2, we need to squeeze the interval. Now, watch what happens as we get closer to t equals 2. Look at that first row. The time interval is from 2 to 3. As we just saw, the change in time, delta t, is 1. The change in position, delta p, is 9 minus 4, which is 5. And the average speed is 5 meters per second. Okay, got it. Now let's squeeze. Let's look at the interval from 2 to 2.1. Now the change in time is just 0.1. The change in position is 4.41 minus 4, which is 0.41. So the average speed is 0.41 divided by 0.1, which is 4.1 meters per second. Interesting. Let's get even closer. The interval from 2 to 2.01. Delta t is now tiny, just 0.01. Delta p is 4.010401 minus 4, which is 0.0401. And the average speed is 4.01 meters per second. Do you see it? The pattern is inescapable. The number is being squeezed towards a single value. What value is it approaching? 4. So, we can make a statement. The limit of the average speed as the time interval delta t approaches 0 is 4. Now this isn't just some abstract algebraic idea. It's a geometric one too. First, think about the secant line. The average speed between 2 points on our curve is just the slope of the line connecting them. Second, as we shrink the interval, as we slide that second point closer and closer to the first one, watch that secant line. It begins to pivot. And third, as it gets infinitely close, it settles into one final, perfect position. It becomes the tangent line, the one line that just skims the curve at that single point. Its slope is the instantaneous speed. Okay, now let's formalize all of this with the proper notation. The limit of the function f of x as x approaches c equals L. Let's connect this notation directly to our car example. Look at this table. First component, LIM, or lim. That just means we're doing the approaching process. Next we have x approaches c. In our example, what was approaching what? Our time interval, delta t, was approaching 0. So for us, it's delta t approaches 0. Then you have f of x. That's the function we are observing. For us, that was our average speed formula. P of 2 plus delta t minus P of 2, all divided by delta t. And finally, L, the limit, the value our function squeezed towards. And what was that value? 4. So, putting it all together, the precise mathematical question we just answered is this. The limit as delta t approaches 0 of the function 2 plus delta t squared minus 2 squared, all divided by delta t, equals 4. We solved this by observing a pattern in a table, but that's not always practical. We need a way to solve this algebraically. We're going to generalize that exact process into a single powerful formula. This formula will take any function, f of x, and forge a new function, f prime of x, that gives the instantaneous rate of change at every single point. This is the master equation of differential calculus. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Let's deconstruct the formula. Check out this table. It's not just a random string of symbols. It's a story. First component in our formula, h. What does it mean? It's just a tiny change in the input. For our car example, this was just delta t, a small change in time. Simple enough. Next up, f of x plus h minus f of x. This is the change in the output, the rise. In our car example, that was p of t plus h minus p of t, just the change in position. Okay, now let's look at the whole fraction. The rise divided by h. The run. It's the average rate of change, rise over run. For our car, this was the average speed over that tiny interval, h. And the most important part, lim. The limit as h approaches 0. What's that? It's the squeeze. It's the process of finding the instantaneous speed from the average speed. And finally, f prime of x. That's the result, the new function for the instantaneous rate of change. For our car, this becomes v of t, the new velocity function. See, it's not a random string of symbols at all. It's a story. The story we just uncovered. Now, for our first boss battle. We are going to derive the derivative of f of x equals x squared using the limit definition from first principles. Step 1. Set up the formula. We just plug our function in. F prime of x equals the limit as h approaches 0 of x plus h squared minus x squared, all divided by h. Step 2. Expand the numerator. We just expand that x plus h squared term. So now we have the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared, all divided by h. Step 3. Simplify the numerator. Now watch this. This is the cool part. We have an x squared at the beginning and a minus x squared at the end. They cancel each other out. This leaves us with the limit as h approaches 0 of 2xh plus h squared divided by h. And cancel. This is the magic step. The whole reason we can't just plug in 0 for h is because we'd be dividing by 0. But now, look, we can factor in h out of the top, giving us h times parentheses 2x plus h divided by h. The h on top cancels the h on the bottom. The problem is solved. We're just left with the limit as h approaches 0 of 2x plus h.
Which brings us to our final move. Step 5. Evaluate the limit. Now that the denominator is gone, it's finally safe to let h become 0. So we have 2x plus 0, which is just f prime of x equals 2x. And we're done. We have rigorously proven from first principles that if f of x equals x squared, its derivative is f prime of x equals 2x. So let's apply this back to our car. The car's position function was p of t equals t squared. Its velocity function, the derivative, is therefore v of t equals p prime of t, which equals 2t. The original question was, what is the speed at t equals 2? V of 2 equals 2 times 2, which is 4 meters per second. It's the exact same number we found by squeezing the intervals. The beast is tamed. We now have a formal algebraic machine that confirms our intuition perfectly. So in this section, we're going to build our foundational library of derivatives. Think of this as our spell book. This is where intuition beats memorization every single time. Let's start with the absolute basics. First up, the derivative of a constant. That's a function like f of x equals c. The formal proof is right here. We take the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, f of anything is just c, so this becomes the limit of c minus c over h, which is the limit of 0 over h, which is just 0. The intuition? A horizontal line has zero slope everywhere. Simple as that. Second, the derivative of a line. Let's say f of x equals mx. Again, we use the limit definition. We get the limit as h approaches 0 of m times the quantity x plus h minus mx all over h. If we distribute that m, we get mx plus mh minus mx all over h. The mx terms cancel out. We're left with mh over h, the h's cancel, and the limit is just m. And the intuition makes perfect sense. A line has a constant slope m everywhere. Now for something special. The number e, which is about 2.718, is the single most important base in all of calculus. The function f of x equals e to the x is its own derivative. Let that sink in. The derivative with respect to x of e to the x. Ice e to the x. This means for the graph of y equals e to the x, the slope of the tangent line at any point x is exactly equal to the value of the function y at that same point.
Let's trace along the curve. We'll check a few points. First, at x equals 0, the value is y equals e to the 0, which is 1. The slope of the tangent line at that point is m equals 1. They match. Okay, let's keep tracing. How about at x equals 1? The value is y equals e to the 1, which is about 2.718. And the slope? The slope m is also about 2.718. They match. One more. Let's go to x equals negative 1. The value? Y equals e to the negative 1, which is about 0.367. And guess what the slope is? The slope m is about 0.367. They match. This property is the very definition of the number e. It is the fundamental language of GrowEarth, which is why it's everywhere in physics, finance, and biology. Next up, its inverse, the natural logarithm. F of x equals ln of x. Its derivative is beautifully simple. The derivative with respect to x of the natural log of x is 1 over x. Let's build the intuition for this one too. We'll trace the graph of the natural logarithm of x. First, let's check a point close to 0, like x equals 0.1. The value, ln of 0.1, is about negative 2.3. But the slope is 1 over 0.1, which is 10. Very steep. Okay, let's move to x equals 1. The value, ln of 1, is exactly 0. The slope is 1 over 1, which is 1. A perfect unit slope. Let's go way out to x equals 10. The value, ln of 10, is about 2.3. But the slope is now 1 over 10, which is just 0.1. Almost flat. The 1 over x function perfectly describes the slope of the natural log. Finally, the trigonometric functions, sine of x and cosine of x. These two are a beautiful pair. The derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. Let's focus on that first one. How is cosine of x the slope of sine of x? Let's trace the sine wave. We start at x equals 0. The value sine of 0 is 0. But look at the graph. It's at its steepest point, going up. The slope is exactly 1. And what's cosine of 0? It's 1. Steepest rise. Okay, let's slide over to the peak. At x equals pi over 2, the value sine of pi over 2 is 1. But at a peak, the graph is momentarily flat. The slope is 0, and cosine of pi over 2 is 0. It's a perfect match. Now down to x equals pi. The value sine of pi is 0 again. But now the graph is falling at its steepest point. The slope is negative 1. And what's cosine of pi? Negative 1. Steepest fall. One last stop at the bottom of the trough. X equals 3 pi over 2. The value sine of 3 pi over 2 is negative 1. But again, it's a trough,
so it's momentarily flat. The slope is 0, and cosine of 3 pi over 2 is 0. It works perfectly. We now have our core library, our essential spellbook. These are our building blocks for everything that comes next.
We've built our foundational library. We know the derivatives of x squared, e to the x, and sine of x. That's great. But real-world functions are messy. The position of an object isn't just t squared. It's something like this. P of t equals 4t cubed minus 5t squared plus 7t plus 10. Now imagine trying to plug that into the limit definition. You'd have the limit as h approaches 0 of 4 times t plus h cubed minus 5 times t plus h squared minus the original function all over h. Ugh, the algebra would be an absolute nightmare. Hard mode. But I'm going to show you how to find the derivative of that entire function in 15 seconds. We're switching to easy mode. To do this, we need our basic toolkit. Just 3 rules. 1, the power rule. 2, the constant multiple rule. And 3, the sum and difference rule. Let's start with rule 1, the power rule. This is the workhorse of differentiation. The formula looks like this. d over dx of x to the n equals n times x to the n minus 1. The algorithm is just 2 simple steps. First, bring the old exponent down in front as a multiplier. Second, subtract 1 from the old exponent to create the new exponent. That's it. Let's see the power rule in action. First up, our input function is x squared. That's already written as x to the power of n. So we apply the rule, n times n minus 1. The 2 comes down in front, so we get 2 times x to the power of 2 minus 1. The result? 2x. Simple. Next one, x to the 5th. Same process. The 5 comes down in front, giving us 5 times x to the 5 minus 1 power. The result is 5x to the 4th. You're getting the hang of it. Okay, what about just x? Well, remember that x is really x to the 1st power, so the 1 comes down. 1 times x to the 1 minus 1 power. And x to the 0 power is just 1, so the derivative is 1. Now for a tricky one, the square root of x. First we have to rewrite it. The square root of x is the same as x to the 1/2 power. Now we apply the rule. The 1/2 comes down, times x to the 1/2 minus 1 power. Our final result is 1/2 x to the negative 1/2 power. Last one, 1 over x squared. We can rewrite this using a negative exponent. That's x to the negative 2. Now, apply the rule. The negative 2 comes down in front, times x to the negative 2 minus 1 power. That gives us negative 2x to the negative 3. It's just a mechanical process. Alright, on to rule 2, the constant multiple rule. What happens when you have a number in front, like 5x cubed? The rule is d over dx of c times f of x equals c times f prime of x. The constant just comes along for the ride. Let's do a quick example. Find the derivative of f of x equals 5x cubed. Step 1. Identify the constant c equals 5 and the function x cubed. Step 2. Differentiate the function part. The derivative of x cubed is 3x squared. Step 3. Multiply by the constant, 5 times 3x squared. The result? 15x squared. See? The 5 just hung out until the end. Here's another one. Find the derivative of g of x equals negative 2 cosine of x. The constant is negative 2. The function is cosine of x. We know the derivative of cosine of x is negative sine of x, so we multiply. Negative 2 times negative sine of x. The two negatives cancel out, and the result is 2 sine of x.
And that brings us to rule number 3, the sum and difference rule. Our final tool lets us break big problems into small, easy ones. The formula is the derivative of f of x plus or minus g of x equals f prime of x plus or minus g prime of x. It means you can differentiate each term one by one, completely ignoring the others. For example, let's find the derivative of h of x equals x to the fourth minus 7x. First, just look at the first term. The derivative of x to the fourth power is 4x cubed. Now look at the second term. The derivative of negative 7x is just negative 7. Now combine them. 4x cubed minus 7. That's our answer. We just took it piece by piece.
Okay, the challenge. Find the derivative, p prime of t, of our original monster function. P of t equals 4t cubed minus 5t squared plus 7t plus 10. Ready? Go. First, we use the sum rule. This means we can do this term by term. We can find the derivative of 4t cubed, then subtract the derivative of 5t squared, and so on. Step 2, let's differentiate each piece. The derivative of 4t cubed becomes 4 times 3t squared, which is 12t squared. The derivative of 5t squared becomes 5 times 2t, which is 10t. The derivative of 7t becomes 7 times 1, which is just 7. And the derivative of the constant, 10, is 0. So, step 3, assemble the final answer. P prime of t equals 12t squared minus 10t plus 7. And we're done. What would have been a nightmare of algebra with the limit definition, we just solved in seconds. This is the power of our toolkit.
We have our basic toolkit. We've totally mastered addition and subtraction. But what about multiplication and division? What about the star and the slash? Let's say I give you this function. H of x equals x squared times sine of x. What's the derivative? It's so tempting to just do them separately, isn't it? But that's not how it works. We need a special rule. Rule number 4, the product rule. This is the one you use when two functions are multiplied together. The formula is d over dx of f of x times g of x equals f prime of x times g of x plus f of x times g prime of x. I know, it looks a little strange, but there's a rhythm to it. Here's how you actually say it. The derivative of the first times the second, plus the first times the derivative of the second. Let's try it on our example. Our example was h of x equals x squared sine of x. We're going to apply the product rule step by step. Step 1. Identify the two functions. The first function, f of x, is just x squared. The second function, g of x, is sine of x. Easy enough. Step 2. Find their individual derivatives. The derivative of x squared, that's f prime of x equals 2x. We know that one. And the derivative of sine of x? From our library, that's g prime of x equals cosine of x. Okay, we have our 4 pieces. Now for step 3. Assemble the 4 pieces using the formula. Remember the rhythm? Derivative of the first times the second. So that's 2x times sine of x, plus the first times the derivative of the second. So that's x squared times cosine of x. There it is, all laid out. Step 4 is just to simplify. H prime of x equals 2x sine of x plus x squared cosine of x. That's it. That's our answer. Not so bad when you follow the pattern, right? Okay, what about division? This one's the big one. It's for finding the derivative of one function divided by another. Something like e to the x divided by x cubed. This is rule number 5. the quotient rule. And look at this formula. d over dx of f of x over g of x equals f prime of x g of x minus f of x g prime of x all over g of x squared. Ugh, now nobody remembers that. Seriously, it's just a mess. But everyone who has ever learned calculus remembers the mnemonic. Here's how it works. The function on top is high, and the function on the bottom is low. So f of x over g of x becomes high over low. And the mnemonic, the little song you sing to yourself, goes like this. Low d high minus high d low over the square of what's below. Say it with me. Low d high minus high d low over the square of what's below. Let's break that down piece by piece. Low is just the bottom function, g of x. D high is the derivative of the top, f prime of x. High is the top function, f of x. And d low is the derivative of the bottom, g prime of x. Finally, the square of what's below is just g of x squared. See? It maps perfectly to that messy formula, but it's so much easier to remember.
All right, let's use it. Example, h of x equals e to the x divided by x cubed. We're applying the quotient rule. Step 1, identify high and low. The high function is e to the x. The low function is x cubed. Step 2, find their derivatives, d high and d low. The derivative of e to the x is just e to the x, so d high is e to the x. The derivative of x cubed is 3x squared, so d low is 3x squared. Step 3, assemble the pieces using our mnemonic. Let's chant it. Low d high. That's x cubed times e to the x, minus high d low. That's e to the x times 3x squared, over the square of what's below. That's x cubed all squared. Perfect. Now we just have to clean it up. Step 4, simplify. The numerator is x cubed e to the x minus e to the x times 3x squared, and the denominator, x cubed squared, becomes x to the 6th. Okay, let's keep simplifying. We can factor out some common terms from the numerator. It looks like both terms have an e to the x and an x squared in them. Let's pull that out. That gives us e to the x times x squared times the quantity x minus 3, all over x to the 6th. We're almost there. We can cancel x squared from the top and bottom. The x squared on top goes away, and the x to the 6th on the bottom becomes x to the 4th. We did it! Now for the payoff. Remember back in our library section, I just gave you the derivative of tangent of x? I said it was secant squared of x. It felt like magic.
It's not magic. We can now prove it. We know from trig that tangent of x is the same as sine of x divided by cosine of x. That's a quotient. We can use our rule. High is sine of x, so d high is cosine of x. Low is cosine of x, so d low is negative sine of x. Let's chant the rule one more time. Low d high minus high d low. Let's plug it in. The derivative of tangent of x equals low, which is cosine of x, times d high, which is also cosine of x, minus high, which is sine of x, times d low, which is negative sine of x. All of that is over the square of what's below, so cosine of x squared. Okay, let's simplify that numerator. Cosine times cosine is cosine squared of x. And sine times negative sine is negative sine squared. But we were subtracting it. A minus and a minus make a plus. So we get cosine squared of x plus sine squared of x. all over cosine squared of x. Now look at that numerator. What is cosine squared of x plus sine squared of x? It's the most famous identity in all of trigonometry. It's 1. Our entire formula just became 1 over cosine squared of x. This is amazing. And what is 1 over cosine of x? That's the definition of secant of x. So 1 over cosine squared of x is just secant squared of x. The derivative of tangent of x is secant squared of x. We've done it. We just proved one of our library rules completely from scratch. See how it all connects? No magic. Just rules building on rules. We can now handle addition, subtraction, multiplication, and division. But we have one final challenge. The boss battle. What do you do with a function inside of another function? Think about h of x equals sine of x squared. Or even worse, h of x equals x cubed plus 5x, all raised to the 7th power. The rules we have can't touch this. Trying to multiply out x cubed plus 5x 7 times would take hours. Ugh, we need a new rule. This isn't just a new rule. This is the rule. This is the master key of differential calculus. It's called the chain rule. It is the single most powerful and common derivative rule you will ever use. Master this, and you've mastered differentiation. The secret? Russian nesting dolls. See functions as an outer function and an inner function. For sine of x squared, the outer function is sine of something. The inner function is x squared. For x cubed plus 5x to the 7th, the outer function is something to the 7th power, and the inner function is x cubed plus 5x. Now here's the chain rule formula. If h of x equals f of g of x, its derivative is h prime of x equals f prime of g of x times g prime of x. Okay, that looks a little abstract, I know. Here's what that means in plain English. First, differentiate the outer function, leaving the inner function completely untouched. Just leave it there. Second, then multiply your result by the derivative of the inner function. You see, f prime of g of x times g prime of x. We have a little saying for this. It goes derivative of the outside times derivative of the inside. That's it. That's the rhythm you need to remember. Derivative of the outside times derivative of the inside. Let's use this master key to unlock these impossible looking problems instantly. Example 1. The polynomial power. Find the derivative of h of x equals x cubed plus 5x all to the 7th power. Okay, we're going to do this step by step. First, identify outer and inner. The outer function, the shell, is something to the 7th power. Its derivative is 7 times something to the 6th power. The inner function, the core, is x cubed plus 5x. Its derivative is 3x squared plus 5. Okay, now let's apply the chain rule. Step 1. Differentiate the outer, keeping the inner. So our result is 7 times, and we just slot that inner function right back in there. 7 times the quantity x cubed plus 5x, all raised to the 6th power. Now step 2. Multiply by the derivative of the inner. We found that the derivative of x cubed plus 5x is 3x squared plus 5. So
The final answer is h prime of x equals 7 times x cubed plus 5x to the 6th power times 3x squared plus 5. Done. No algebra nightmare. Just a clean two-step process. This is the power of the chain rule. Okay, example 2, the trigonometric function. Let's find the derivative of h of x equals sine of x squared. Step 1, identify outer and inner. The outer function is sine of something. Its derivative is cosine of something. The inner function is x squared, and its derivative is 2x. Alright, step 2. Let's apply the chain rule. Derivative of the outer, keeping the inner, is cosine of x squared. Now, multiply by the derivative of the inner, which is 2x. The final answer is h prime of x equals cosine of x squared times 2x. We usually write the polynomial part first, just for neatness. So the final answer is written as h prime of x equals 2x times cosine of x squared. With the chain rule in our toolkit, we can differentiate almost any function you'll encounter. Our set of tools for y equals f of x is now complete.
So far, we've been dealing with functions that are really, well, nicely behaved. We call this explicit. Y is explicitly defined in terms of x. It's pretty easy. You've got things like y equals x squared, or maybe y equals sine of x divided by e to the x. You can always get y on one side and all the x stuff on the other. But what about relationships where x and y are all tangled together, where you can't easily get y by itself? Think about the equation of a circle. X squared plus y squared equals 25. This is an implicit relationship. If you try to solve for y, you get this mess. Y equals plus or minus the square root of 25 minus x squared. It's messy. It's not one function, but two. It's a pain. This is where we learn to hack the system. What I'm about to show you isn't a new rule. Not at all. It's a clever application of the chain rule that lets us solve problems that look impossible. It's called implicit differentiation, and it feels like a cheat code. Here is the entire trick. The one key idea you need to remember. We're going to take the derivative of equations with respect to x. First, when we see an x term, like x squared, we differentiate it normally. The derivative of x squared is just 2x. Simple. Second, when we see a y term, we have to remember that y is secretly a function of x. So the chain rule must apply. Let's look at this, the standard rule. The derivative with respect to x of x squared is just 2x. Now for the chain rule application. What's the derivative with respect to x of y squared? Well, the outer function is something squared, so its derivative is 2 times something. The inner function is y, so its derivative is dy dx. So, the final answer is 2y times dy dx. That's it. That is the entire hack. Every time you differentiate a term with y, you do it normally, and then you must multiply by dy over dx because of the chain rule. Here's the algorithm. It's 4 simple steps. 1. Take the derivative of both sides of the equation with respect to x. 2. When you differentiate a term with y, remember to multiply by dy over dx. 3. You'll get an equation with x, y, and dy dx all mixed up. Don't panic. 4. Just use algebra to solve for dy dx. Let's do an example. Example 1. The slope of a circle. We want to find the formula for the slope dy dx of the circle x squared plus y squared equals 25. Step 1. differentiate both sides with respect to x. So we take d dx of x squared plus y squared and set it equal to d dx of 25. All right, now for step 2. Let's go term by term. The derivative of x squared, that's 2x. Easy. The derivative of y squared. This is our key trick. It's 2y times dy dx. And the derivative of 25? That's just 0. Our new equation is 2x plus 2y times dy over dx equals 0.
Okay, last part, step 3. Now we just solve for dy dx. We subtract 2x from both sides to get 2y dy over dx equals negative 2x. Then we just divide by 2y, and we get dy by dx equals negative x over y. This is our answer. But does it work? Let's not just trust it. Let's prove it. Let's test a point. How about the point 3, 4? According to our formula, dy over dx equals negative x over y. So the slope at 3, 4 is negative 3/4. Looking at the graph? Yeah, that looks plausible. Okay, test point 2, 0, 5. This is the very top of the circle. The tangent line should be completely flat. The slope should be 0. Our formula gives us dy over dx equals negative 0 over 5, which is 0. It works perfectly. One more. Test point 3, 5, 0. This is the far right side. The tangent there should be vertical. The slope should be undefined. Our formula gives us dy dx equals negative 5 over 0. Division by 0. It's undefined. The hack works. It gives us the correct slope at every single point on the circle. Are you ready for your victory lap? Let's use this clever trick to do something amazing. Back in section 3, I just gave you the derivative for arcsine of x. It was 1 over the square root of 1 minus x squared. It felt like it came from nowhere. Like magic.
We're about to kill the magic. We are going to derive it ourselves, right now. The victory lap. Finding the derivative of arcsine of x. The problem is, find the derivative of y equals arcsine of x. Okay, first we rewrite it implicitly. If y equals arcsine of x, that's the same thing as saying sine of y equals x. Now this is something we can work with. Okay, step 2. Differentiate both sides with respect to x. On the left side, the derivative of sine of y becomes cosine of y times dy over dx. On the right side, the derivative of x is just 1. Our new equation is cosine of y times dy over dx equals 1. Step 3. Solve for dy over dx. We just divide by cosine of y. We get dy over dx equals 1 over cosine of y. We're so close. This is the right answer, but it's in terms of y. We need it in terms of x. Time for a quick trip to trigonometry. We know that sine of y equals x. Let's visualize this with a right triangle. Imagine an angle y. Sine is opposite over hypotenuse. So if sine of y is x over 1, the opposite side is x, and the hypotenuse is 1. Using the Pythagorean theorem, the adjacent side must be the square root of 1 squared minus x squared. So what's cosine of y? It's adjacent over hypotenuse. That means cosine of y equals the square root of 1 minus x squared. Now for the final step, we substitute our finding for cosine of y. Our derivative was dy over dx equals 1 over cosine of y. Our triangle just showed us that cosine of y is the square root of 1 minus x squared. So we get dy by dx equals 1 over the square root of 1 minus x squared. And there it is. We have just proven the derivative of arcsine of x. It's not a magic formula you need to memorize. It's a direct, logical consequence of the chain rule, a consequence that you now have the power to derive yourself. We have built the entire machine, from the limit to the basic rules, to the master key of the chain rule, to this clever hack of implicit differentiation. Our toolbox is complete.
Look at this, your completed toolbox. From one simple question about a car's speed, we built the entire machine of differential calculus. You didn't just memorize formulas, you built every single rule from the ground up. The basic rules, the essential functions, the trigonometric derivatives, the product rule, the quotient rule, the master key chain rule, even the clever hack of implicit differentiation. You now possess the complete toolkit for differentiation. The promise from the beginning, fulfilled. So what's next? Integral calculus, the other half of the story. You've built the machine. Now go use it.